What if I told you that light, the very thing that allows us to perceive the world, has hidden characteristics that play an essential role in our daily lives? Yes, light. It's not just about illuminating our surroundings or enabling us to see the rich colors of a sunset. Light, in its essence, is an electromagnetic wave, an energy form that exhibits characteristics of both particles and waves. Imagine a pond on a calm day. You toss a pebble into it, and it creates waves, rippling outwards in concentric circles. Now imagine those waves in a three-dimensional space, moving forward and oscillating up and down, left and right, in a myriad of directions simultaneously. That's a simplified way of visualizing light as it naturally occurs. But let's delve a bit deeper. Light, as an electromagnetic wave, is composed of electric and magnetic fields oscillating perpendicular to each other. Picture two dancers moving in sync, but always in opposite directions. One moves up as the other goes down, one sways left as the other veers right. They never collide or disrupt each other's flow. Instead, they create a harmonious dance, moving forward together. This interplay, this dance, is what gives light its wave-like properties. Yet there's an aspect of light that often goes unnoticed, a characteristic that's not visible to our naked eyes but has profound implications in various fields, from physics to biochemistry, from telecommunications to photography. This characteristic is polarization. Polarization, in essence, is the process by which the multi-directional oscillations of light's electric field get confined to a single plane. It's as if our dancers, who were previously free to move in any direction, are now restricted to a single plane. Their dance becomes more ordered, more predictable, yet just as beautiful. This, at its core, is the concept of polarized light. Dive with me into the fascinating world of polarized light, where we'll uncover the secrets of light that often go unnoticed. To comprehend the concept of polarized light, we first need to understand what polarization means. At its core, polarization is a process that limits the direction of the electric field in a light wave to a single plane. Picture a rope tied to a pole. If you move the rope up and down, the wave travels along the rope in one direction, similar to how light waves move when they're polarized. Now, there are three main types of plane polarized light: linear, circular, and elliptical. Linear polarization, as the name suggests, involves light waves vibrating in a single plane. Imagine a sheet of glass with vertical slits. When unpolarized light passes through these slits, only the waves aligned with the slits can get through, creating linearly polarized light. Next up is circular polarization. This involves light waves rotating in a circular motion as they move forward. To visualize this, think of a corkscrew moving along a straight line. The rotation can be either clockwise or counterclockwise, and each rotation corresponds to a single wavelength of light. Lastly, we have elliptically polarized light, which is a bit more complex. It's similar to circular polarization, but instead of a perfect circle, the light waves trace out an ellipse as they move forward. This happens when linearly polarized light passes through a quarter wave plate at an angle, altering the phase difference between the two perpendicular components of the light wave. These different forms of polarization are not just scientific curiosities. They have practical applications in various fields, including communications, photography, and even 3D cinema. So we've learned that light isn't as simple as it seems, right? But there's more to it. Let's delve into optical activity next. Scene script. Ever wondered what happens when plane polarized light meets certain substances? It dances. Welcome to the fascinating world of optical activity, a phenomenon where certain substances can twirl the plane of polarization of light passing through them. Imagine this like a salsa dancer elegantly twirling their partner around the dance floor. Optical activity is not a universal trait, though. It's exclusive to chiral substances. A chiral substance is one that cannot be superimposed on its mirror image, much like your left and right hands. These substances have the unique ability to rotate the plane of polarized light, and this rotation can happen either to the left, which we call levarotation, or to the right, which we term dextrorotation. But what factors influence this captivating dance of light? First, the nature of the dancer, that is, the substance itself. Different substances have different abilities to rotate light, and this is called their specific rotation. Secondly, the concentration of the substance. Just as a dance floor full of people would cause a more chaotic spin, a higher concentration of a chiral substance will cause a greater angle of rotation. Thirdly, the path length, or the distance the light travels through the substance. Think of it as the length of the dance floor. The longer the floor, the more room there is for spinning. Finally, the wavelength of light used. Different wavelengths, or colors of light, can be rotated to different extents. It's akin to changing the rhythm of the music and seeing how the dancers adapt their movements. The measurement of this rotation is typically done using a device called a polarimeter, which allows us to quantify the angle of rotation and, in turn, determine the concentration of the chiral substance in a solution. So, just like humans, light too can perform a dance when it interacts with certain substances. Intriguing, isn't it? Now, let's explore how this knowledge of light's hidden dance helps us in the real world. To start with, let's talk about measuring polarized light. By passing light through a polarizer and an analyzer, we can determine the degree of polarization. But how does this apply to practical scenarios? Well, enter the concepts of specific and molecular rotation. Specific rotation is the rotation of plane polarized light per unit length per unit concentration by a solution of a compound. It's a fundamental property of chiral molecules, and its measurement can be used to determine the concentration of such molecules in a solution. Molecular rotation, on the other hand, is the rotation of plane polarized light by 1 mole of a substance in a specific volume. Now, let's turn our attention to a device called a polarimeter. This instrument measures the angle by which a substance rotates the plane of polarization of light. It's an incredibly useful tool in fields such as chemistry, biology, and pharmaceuticals, helping scientists to study chiral molecules, monitor sugar content in food and beverages, and even determine the purity of certain drugs. Next, let's delve into 3 fascinating phenomena: optical rotatory dispersion, circular dichroism, and the cotton effect. Optical rotatory dispersion, or ORD for short, is the variation of specific rotation with the wavelength of light. It provides us with valuable information about the 3-dimensional structure of chiral molecules. Circular dichroism, on the other hand, is the difference in the absorption of left-handed and right-handed circularly polarized light. It's a powerful tool in biochemistry and biophysics, allowing researchers to study the secondary structure of proteins and other biomolecules. Last, but certainly not least, we have the cotton effect, named after the French scientist Aimé Cotton. This effect refers to the presence of a peak, or trough, in the circular dichroism spectrum of a chiral molecule. It occurs at the wavelength where the molecule's specific rotation changes direction. The cotton effect can provide scientists with key insights into the stereochemistry of chemical reactions. As you can see, the subtle dance of light is not just a mesmerizing spectacle. It's a fundamental aspect of our world, underpinning a wide range of scientific and industrial applications. Whether it's helping chemists to understand complex molecules or enabling the food and beverage industry to ensure product quality, the power of polarized light is truly remarkable, and that's just scratching the surface. There's so much more to discover and learn about this fascinating field. So stay curious, keep exploring, and remember, the more you know about the world, the more fascinating it becomes. As we've seen, the dance of light is not just a fascinating spectacle, but it's also incredibly useful in various scientific and industrial applications. As we conclude our exploration, let's summarize what we've discovered about the hidden dance of light. We've journeyed from the very nature of light, understanding how it can be polarized into linear, circular, and elliptically polarized forms. We've moved into the realm of optical activity, exploring how substances can rotate this plane polarized light and the factors that affect this angle of rotation. We've even delved into how this polarized light can be measured and the significance of specific and molecular rotation. And let's not forget the intrigue of the polarimeter, an instrument so crucial in observing and measuring this dance. We've also touched on the fascinating phenomena of optical rotatory dispersion, circular dichroism, and the cotton effect, and how they find applications in various fields. And there you have it, a glimpse into the fascinating world of light's hidden dance. Subscribe for more, because you won't find me later.